on my head, which is keeping the hair out of my eyes. So thank you so much for being here. Welcome to this live. Let's press some buttons to make sure this is working. Indeed it is. Indeed it is. Good evening, good afternoon, good night, good morning, good mid-afternoon, good mid-evening to wherever you are joining from. Australia, New Zealand, Antarctica, Europe, Asia, Africa. I do hope you are here right now and about to be joining us right now. And North America, South America, you are fine too. I hope you are already here right now and joining right now. Steven Spears is here and saying, hey, Audrey. Hello, Steven. How are you? I hope you're having an excellently, massively amazing and successful day. How are you doing? Today we will be talking about particle physics. Yesterday, as you know, we started off with the quantum mechanics discussion. We talked about the uncertainty principle with the help of the book written by an extremely successful person, Stephen Hawking, A Brief History of Time. And that gave us an introduction to quantum physics, quantum mechanics, and how it is kind of quite a bit different from classical mechanics and the deterministic nature of classical mechanics and all that stuff. I just say you on, and I'm the first in the room. You are. Stephen, you are here. Me, I am here. It is us rocking and rolling. I hope that you're ready. It is you and me right now. Indeed it is you and me, but I have to keep talking like this, otherwise more people will not be joining. So I have to be like, okay, class is on, guys. Class is gone, you're getting late. Get here, get started. So, Stephen, are you ready? How's your day? Let me have some water while I talk to you. BRB thirsty. Oh my gosh, look at this. I have water for you as well. Perfect. No, purified drinking water from Walmart right here, Stephen, right here. I wish I could offer you some through the screen. Indeed I do, but let me keep talking. The situation is that we spoke about, of course, we're covering Brief History of Time by Stephen Hawking. It's a very physics-filled week this week. Every night we're covering a new physics topic with the help of this book. Let me show you the book right here. Brief History of Time by Stephen Hawking. And of course, we talked about expanding universe one of these nights, and that was lovely. Tired, worked in my yard today. I'm good, and you? I'm good too. I am also tired. I don't know what it is. It's a Wednesday and I'm tired. But anyways, we talked about, see how this is black, and I thought my hair was black, and now this black is different from my hair black. Anyways, hi. How are you? Welcome, Miles C. Miles C says here. Hello. BMW says hi. Hello, BMW. I hope you're selling a car today. Steven Spears says, hey, Miles. Miles says, hey. Lester Jones says hi. Hello, Lester. Hello, Miles. Hello, Steven. Hello, BMW. Hello, Mercedes. Hello, Porsche. Hello to everybody, one and all. Welcome, one. Welcome, all. BBY Girl says, are you real? Am I real? Are you real? Am I real? I think I'm real. Should I click on some kind of, do I do the patterns of like, check how many boxes have a car in it type of thing, in order to prove that I am real? Indeed, I am real. I can read and I can speak and I can think most of the time, unless I'm sleeping. Steven Spears, even then I'm thinking about you guys and this live and physics and astronomy, and we will be continuing to continue. So, Steven Spears says, hi, BMW. Hi, Lester. Kraken from the trench says, you're beautiful. Oh, thank you, Kraken. Steven Spears says, hello, all. Reverse like. BBY girl, OMG girl, your skin is so flawless. Oh, thank you. Evil eye remove, and thank you. Thank you, the genetics. Thank you, grandma. Thank you, mama. Thank you, mother. Thank you, daddy. Thank you. Thank you, I guess, to the biology for that. Kraken from the trench says, you're beautiful. OMG. Thank you. The athlete. What's happening here? We will be talking about quantum mechanics and particle physics today. Actually, we already talked about quantum mechanics, a bit of an introduction. We talked about uncertainty principle last night already. The athlete, hello. Verse says, Chickpea, hello. Andrew, hello. We meet again. The way you speak, I'll give you the world yesterday. Oh, thank you. Thank the chickpeas. The chickpeas also thank you. Thank you. Thank you. Thank you, chickpeas. Thank you, plants. Thank you. In fact, did you know? Did you know we must thank the plants because the plants have put more oxygen into the atmosphere. We had a much more carbon dioxide filled atmosphere in the past. Oceans have helped with that. Oceans, the water, liquid water, has helped to remove carbon dioxide from the atmosphere and turn it into rocks. And also then plants have added more oxygen, making the earth more breathable, more nice for us to live on. And so indeed we must all thank the chickpeas and the plants. Hello, beautiful, is my first time here. Hello, Eber Navas. Hello, Savin Rebe. I don't know if I'm supposed to read that forwards or backwards, so I tried both. Hello, Eber. Hello, Tony. Tony, be careful. My mods may just put you on timeout. So just try to be a little bit more, I don't know, normal, as in a little bit more kid friendly, if you will. I have kids who are mods and they may not like certain words from you. Tony Kolibali, 908 VR123. Hi. Hello, 908 VR123. I love that this name is filled with numbers. The athlete, let's go. Even a weed plant. Weed is okay if it's a plant. Sure, why not? Hi, because 10x times. Ha ha ha. Nathan Mullins, hello. Felipe, hello. You look fresh out the brain, Jim. Oh my gosh. Oh my gosh. I was in the gym. How do you know, Ver? How do you know? Indeed, the gym has brought me here. Without the gym, there would be no me right here, right now. Tony says hello with certain emojis. Love it. Hello, Tony. Hello, 908. Chicken butt. Hello. Andrew, hello. Stephen, hello. 908, hello. Tony says French kiss. Tony, you are going to be in so much trouble. Much trouble. I am warning you now. I am the kind one. My mods are not. As soon as they join, you may just see yourself in a punishment type of place in this classroom. So anyway, where's Reese? I don't know. I don't know where he is. Actually, I don't know. It's late or early for him. So reply. Reply to what? Hello, 908. I know you came from the gym because I'm a mod who isn't a mod yet. Aww. Oh my goodness. Do you want to be a mod? I mean, I feel like I have too many already. They are putting a lot of people on timeouts. If all my subscribers are either on timeout or a mod, I don't know. Ooh, also please do like and subscribe. Thank you so much. Thank you. Welcome to this live, and please do like and subscribe right here, right now. share and subscribe, and share with a friend, and share with your family members, and share with your secretary, and share with your boss. And thank you so very much. Like and share and subscribe. It's all cool. You've got a lot. Yes, I do. I have a lot of mods and people who need to be modded. I'm strong. I went to the gym. Good job, 908. Felipe says you're so cute and funny. Thank you. Can we get 20 likes? Thank you so much. So I do not know how to behave, or for that matter, misbehave. I'm a bad boy. Steven, you are the baddest boy as well as the most well-behaved boy on this chat, usually. Generally, your comments have to do with the topic, which is really nice and refreshing, except for when you're being bad with Doro and Reese. It is true. You guys talk about the Titanic, which is fine too. You know what? I hope the Titanic sponsors my life one of these days, as soon as the Titanic decides to float again as a ship. Haha. Anyway, I do like ships and cruises and boats and things like that. So if a boat wants to sponsor me, go right ahead. I will not mind at all. Not at all. I hope there's food on the boat. My comments have to do with stoves and how you hardly use. So you will be happy to know that my stove has been used recently by people who visit me. Indeed, they visit and they cook, and they found the stove to be functioning. Thank you, universe. Thank you so much. Thank you so much. You know, they're building a second Titanic. No R. Kelly. I am not Kelly. Is that what you're saying, Tony? I am indeed not a Kelly. Ver says, ha ha. Good, good. Laughing is a good thing. I don't know. I did not know they're building a second Titanic. Should we be on it once it's built, or should we just spectate at it as it's being built and then leave it alone because we know what happened to Titanic #1? What do you think, Stephen? So anyway, yesterday, how do you season your chickpeas? Oh my gosh, Ver, you have to come to one of my chickpea lives. First I put the chickpeas in the microwave. Then I make sure that they are quite hot. Then I put ghee on it. Ghee, as an Indian desi ghee on it. Then I mix it up. Then I put lao gan ma, chili flakes, into the whole thing. Then, if I remember, I put some cheese on it. And then, if I remember, I put some pepper in it too. Maybe. Then I start eating it because by then I'm famished. Just so hungry. Just so hungry that I can think no more. Just so hungry. That's why I eat the chickpeas in whatever way suits the moment. Whatever way the suits us the moment. I will admit my favorite Titanic movie is Ray's Titanic. What does that even mean? Is there such a movie, Stephen? I don't know much about the movies made in Hollywood. So I don't know. I just don't know. I only know about telenovelas. Actually, I'm kidding. I know some telenovelas. I only know about Indian movies and shows more than Hollywood. More than Hollywood. I did not know Indian women can be so adorable. What do you mean? Most women at this point will be Indian, and yes, I hope that we are adorable. Yes, we are adorable. By birth. If we are allowed to be born, that is. Some of us are not. Some of us are indeed not. Not funny, but a reality. The microwave, yeah, I know what's ghee, sounds edible. It is extremely edible. By the time it's in my stomach, it has been edibled. It has been edited. It has been eaten, whatever the word is. Okay, so you know what? Without further ado, as the clock strikes 11:11 here in the Boston Eastern time zone, I think I will go ahead and start the topic of the day, which is the particle physics topic. And I will just remind you that we've been talking a little bit about cosmology, astrophysics, and the universe from the lens of Stephen Hawking, who wrote the book, of course, A Brief History of Time. And we saw how this sort of general theory of relativity, more classical approaches, is great for large-scale understanding of the universe. But at some point, we must sort of revisit what is missing from that picture, and what was missing is actually quantum mechanics, and how Einstein didn't really incorporate quantum mechanics into his theory of general relativity. And we got some questions that we had to answer, such as, do we need to come from a singularity like the Big Bang? Did we actually come from it? Could it have happened versus should it have happened? And then we named a couple of singularities, of course, which is the Big Bang, and also black holes. Those are a singularity as well. And if general theory of relativity is not incorporating quantum mechanics, basically, general theory of relativity is not completely correct. It is a good theory. It has helped out a lot with an updated understanding of gravitation, but it's not totally, completely correct. And then we also looked into quantum mechanics, which seems very bizarre to a lot of the more classical physicists. It did seem very bizarre. It had these very different aspects to it, such as probabilistic nature of it, the fact that you need the uncertainty principle, and no matter how well you do a measurement, no matter how good your experiment is, there is always this uncertainty limit on the accuracy with which you can measure both position and velocity of a particle. And we talked about that, and how the uncertainty principle is the fundamental truth of nature when you're doing quantum mechanics, when you're dealing with small scales of things like particles within an atom and such. So we talked about that. And that kind of launches us into the next step, which is particle physics. And I will mention that no matter how much people disliked the bizarreness of quantum mechanics, no matter how uncomfortable it might have made people, especially who are used to more deterministic nature of physics and getting deterministic results and answers. Let me, my brightness was really low. Let me change that. Sorry, 1 second. No matter how much discomfort it may cause, quantum mechanics is actually very, very, very successful. And why? How is it successful? It matches with what we see in experimental science, what we see experimentally in physics and beyond. And it has now grown to much beyond just quantum mechanics. In the later part of the 20th century, we saw the emergence of particle physics, and now we're going to talk about a bunch of particles and the fundamental forces of nature. You will see how particle physics gives us a description for all the fundamental particles, as well as gives us a way of categorizing all the particles, and also tells us about the fundamental forces of nature. Neutrinos, yes, that is a fundamental particle. Baji, secretly reading your books and about to build a highly intelligent interface that explains everything about the unknown mysteries of the universe in extreme detail. Exactly. Ace Wolf Peach, hello. Thank you for liking the live. Where is Baji? He's usually behind me on that cat tree, but right now he is somewhere else. They just got a snack right before I started so that they would not so that they would be okay for a bit. Hello, thank you. Hello. Thank you for liking the live. Baji will probably join me behind me soon here. So, before I have talked about the particles on this channel. I love your energy tonight and the hair looks nice. Thank you. We have talked about the particles, the fundamental categories of particles. So these are, if you remember, these were basically leptons, quarks, and bosons. So we've kind of given examples of the leptons and examples of the quarks and examples of the bosons. Today we will read about this from the perspective of Stephen Hawking, which will be really nice. I think he's probably done a good job of summarizing all of this information. And so far the book reads really easily. So I think this will be good review, but we have actually touched upon the particles and the fact that, quantum mechanics continued to be successful and gave us this whole thing, this whole other part of physics, which is the standard model of particle physics. And we've got these three categories of particles that we have talked about. Leptons, once again, lepton example would be neutrino. Somebody said neutrino in the chat. An electron is also an example of a lepton. Another category of particles is quarks. Again, quarks is something we are also familiar with because the subatomic particles within a nucleus of an atom, protons and neutrons, actually further break down into quarks, as in even more fundamental particles or quarks make up those things such as protons and neutrons. In cosmology, protons and neutrons are sometimes categorized together as baryons. So you've heard about that. These are just different names sometimes for the same thing. So don't get them confused. Baryons are nothing but protons and neutrons. And quarks are the more fundamental particles that make up protons and neutrons. So that's a category, quark. But there are other types of quarks as well. So quark is one of the fundamental categories. And then there's another fundamental category, which is bosons. And these, as you will see, are carriers of the fundamental forces. And we will get a lot more detail from the chapter today, which is called Elementary Particles and the Forces of Nature by Stephen Hawking. So that was a little bit of a preview. I also wanted to remind you that we've talked about this in the past, so maybe some of this will be like a review, and hopefully that helps, and you will get a more formal introduction today from this book, and hopefully that helps, and I'll get started. I love your energy tonight and the hair looks nice, said Nathan. Hello, Nathan. Hello, Ver. So neutrinos interact through the weak force, which is carried by the W and Z bosons. Yes. So there is different types of bosons. The name boson comes from a scientist whose last name is Bose, B-O-S-E. kind of like the headphones, I believe also has the same name, Bose headphones. But there is a scientist, there was a scientist actually from same city where I'm from, Kolkata in India, who worked with Einstein on, actually he worked independently and also collaboratively with Einstein. And the type of particle bosons is named after him, after his last name, Bose. And bosons, there are different types. So see the three categories were leptons, quarks, and bosons, right? So bosons have different types of particles under that category. Bosons, photons is an example of bosons. So electromagnetic waves or light wave. The particle nature of light is called photon, for example. Sometimes we say quantum of light, but really the name given is photon. And then, as you said, neutrinos go with bosons. Yes, so neutrinos are very elusive, introverted type of leptons that do not interact much. But when they do interact, they interact through what we call the weak force. They don't interact through electromagnetic force. They don't interact with strong force. They don't interact, with basically they don't interact much outside of just the weak force. And the weak force is carried with the two types of bosons, W and Z bosons, which we'll, I think, probably get some more information about from this chapter. So yeah, if you're interested, neutrinos don't interact with, for example, with electromagnetic waves, with photons, and electrons do. Other types of leptons do, neutrinos don't. So that's sort of an example. We will get a review of all of this, but yeah, that is an example. Neutrinos being a lepton that interact with each other through the W and Z bosons is an example of some of this. Came out to watch you play. Hello, Batman. Hello, Steven. Hello, Ver. I have missed you. Okay. Hello, Alex. I miss you, says Alex. Hello, Alex. Hello, darling. How are you? Tucks away my freeze gun. Aww. Hello, Batman. I see you're at it. Goodness. Batman. Listening to you and watching Star Trek Voyager, I'm a Trekkie. Oh, you like Star Trek? Oh, nice. Good. Yeah, keep on listening. Here we are. So, without further ado, after giving you that little bit of introduction, oh shoot, you know what? I have not shared the live. I will take a sip of my water and get started with elementary particles from the book here. And thank you so much for being here, and thank you for liking the live. And I need to share the live. I think you will like today's subject. It's a little quiet today, but nevertheless, I'm gonna get food and I'll be back to gain some knowledge. Go ahead. Keep it on. Keep us on while you're getting food. Keep it going, Ver. Okay. Yay. Nathan, hello. That's okay. Sometimes it's just me and one other person, yes. No worries. I'm trying to share the live still. I have to use this other phone to do that. Do not make me ask my favorite sci-fi question now. I love Star Trek. Well, Steven, you have a Star Trek friend. Go ahead. Make friends with Nathan. Combat sports. Hello, Steven. Hello, Ver. Hello, Combat Sports. Hello, Batman. Steven, I think you will find a friend today. A new one. It's Nathan. Okay. Oh gosh. Oh my goodness. It's the phone is having this phone only works sometimes. Nathan says question mark. What are you question marking about, Nathan? Hi, like and subscribe. I'll put that down. Pin that message. I do have an arch enemy, Batman, and I'm the Joker. Steven's question. Oh, yeah. Nathan is asking, Steven, what did you mean? I will say, we are live. Okay. Aristotle believed that all the matter in the universe was made up of 4 basic elements: earth, air, fire, and water. Who knows this? Earth, air, fire, and water. These elements were acted on by 2 forces: gravity, the tendency for earth and water to sink, and levity, the tendency for air and fire to rise. Yes, we will talk about quarks in a minute. Yes, we were just mentioning them, but yeah. This division of the contents of the universe into matter and forces is still used today. Aristotle believed that matter was continuous, that is, one could divide a piece of matter into smaller and smaller bits without any limit. One never came up against a grain of matter that could not be divided further. A few Greeks, however, such as Democritus, held that matter was inherently grainy and that everything was made up of large numbers of various different kinds of atoms. The word atom means indivisible in Greek. Indivisible. Turns out that atom, there are more subatomic particles, but at that point, I guess they thought that atom was indivisible. No more dividing an atom, but it can be. Now we know. For centuries, the argument continued without any real evidence on either side. But in 1803, the British chemist and physicist John Dalton pointed out that the fact that chemical compounds always combined in certain proportions could be explained by the grouping together of atoms to form units called molecules. Let's continue the atom book sometime. Yes, of course. Yes, I still have the atom book. I wish I could find the physical copy though. I just have the book on my phone, on my app. But yes, good to know that you want the atom book. Perfect. So John Dalton pointed out the fact that chemical compounds always combined in certain proportions and could be explained by the grouping together of atoms to form units called molecules. However, the argument between the 2 schools of thought was not finally settled in favor of the atomists until the early years of this century. One of the important pieces of physical evidence was provided by Einstein. In a paper written in 1905, so if you remember our discussion of Einstein from the book Einstein's Cosmos by Michio Kaku, Einstein was very productive in this year, 1905. So we're going to get a look again at this particular year. So in a paper written in 1905, a few weeks before the famous paper on special relativity, Einstein pointed out that what was called Brownian motion, the irregular random motion of small particles of dust suspended in a liquid, could be explained as the effect of atoms of the liquid colliding with the dust particles. So that's really what Brownian motion was. So Brownian motion was already discovered, but Einstein gave us further insight. By this time, there were already suspicions that these atoms were not, after all, indivisible. So again, lots of progress in quantum mechanics in the same century as Einstein is doing all of this, in the 20th century, told us that atoms were actually divisible, as in there were further subatomic particles. But lots and lots of progress happened on this during that same time, or about to. Several years previously, a fellow of Trinity College, Cambridge, J.J. Thomson, had demonstrated the existence of a particle of matter called the electron. So I don't know if you guys read about J.J. Thomson in like physics class or something, but he gave us something called the electron. And there were lots of early sort of models of the atom and things like that. Okay. Hopefully we will get some of that here today to kind of summarize everything. So J.J. Thomson had demonstrated the existence of a particle of matter called the electron that had a mass less than 1,000th of that of the lightest atom. He used a setup rather like a modern TV picture tube. A red-hot metal filament gave off the electrons, and because these have a negative electric charge, an electric field could be used to accelerate them toward a phosphor-coated screen. When they hit the screen, flashes of light were generated. Soon it was realized that these electrons must be coming from within the atoms themselves. And in 1911, the New Zealand physicist Ernest Rutherford finally showed that the atoms of matter do have internal structure. They are made up of an extremely tiny, positively charged nucleus around which a number of electrons orbit. Ariel, hello. Yes, thank you, Combat Sports. Very nice comment on Brown in Motion. Yes, vegans are allowed. Thank you for liking the live. Can we get 10 likes? Thank you. Hi, Ariel. Can we get a super chat? Oh, wow. Look at you, Ver. Thank you so much. Thank you. So, Ernest Rutherford finally showed that the atoms of matter do have internal structure. They are made up of an extremely tiny positively charged nucleus around which a number of electrons orbit. He deduced this by analyzing the way in which alpha particles, which are positively charged particles given off by radioactive atoms, are deflected when they collide with atoms. At first, it was thought that the nucleus of the atom was made up of electrons and different numbers of a positively charged particle called the proton, from the Greek word meaning first, because it was believed to be the fundamental unit from which matter was made. So at that point, they were like, oh, maybe proton is the fundamental unit. You know, this whole discussion about quarks that we will get into, we still had not discovered quarks, right? We just barely discovered the electron and nucleus and all that. So, however, in 1932, a colleague of Rutherford's at Cambridge, James Chadwick, discovered that the nucleus contained another particle called the neutron. So until they discovered the proton, they thought, okay, electron, proton, that's about it. Like proton is the majority. It's in the nucleus. The nucleus has the most mass, so maybe the fundamental building blocks is the proton. But then they found also this other particle, different particle called the neutron. Thank you so much. Thank you, Stephen. Thank you, Ver. Thank you, Ariel. So Chadwick received the Nobel Prize for his discovery of the neutron. So yes, quiz questions I will ask you later. Who discovered the neutron? And again, it is 1932, the year a colleague of Rutherford's at Cambridge, James Chadwick, discovered that the nucleus contained another particle called the neutron, which had almost the same mass as a proton, but no electric charge. No electrical charge, but almost the same mass as the proton. Chadwick received the Nobel Prize for his discovery, as was elected Master of Gonville and Caius College, Cambridge, the college of which I'm now a fellow. So Stephen Hawking is a fellow of this. He later resigned as master because of disagreements with the fellows. There had been a bitter dispute in the college ever since a group of young fellows returning after the war had voted many of the old fellows out of the college offices they had held for a long time. So looks like there was a disagreement, and Chadwick fell out with the fellows. This was before my time. I joined the college in 1965 at the tail end of the bitterness, when similar disagreements forced another Nobel Prize winning master, Sir Neville Mott, to resign. Looks like there was some drama at Cambridge. Hello, Doro. My water break will be a bit later, actually, so you are early. Once my water break actually starts, you can say that. Yes, neutrons and protons are made up of quarks. Combat Sports is giving us some preview into quarks. How nice. Wow, there is an alias present here. Love it. Love it, love it, love it. Thank you so much. Water break, can you please like the live? Thank you so much. Can we get 20 likes? Water break, please, water, like the live. Reese, hello. Please do like the live. Give us 10 likes. 20 likes or bust. So, yeah, there was some drama in Cambridge where people were resigning or fighting based on the bad blood that they felt, which there is no bad blood here at all. At all. Even though there is a water break, there is no bad blood. Mod the account. Chickpea break. Oh my gosh. Up to about 30. No. You're going to learn a little bit more particle physics before we have a break. I had to hit the bathroom at 1 p.m. I returned at 11 p.m. Oh gosh. Up to about 30 years ago, it was thought that protons and neutrons were elementary particles, but experiments in which protons were collided with other protons or electrons at high speeds indicated that they were in fact made of smaller particles. And I believe Combat Sports has already told us about that actually they break down into quarks, but we will get into it in more detail here. Thank you so much for being here. Thank you so much for liking the live. Thank you. Welcome to this live. What you got? This is a hairband. It keeps the hairs away from my face. Thank you for liking the live. Reese, did you like the live? I don't see 10 likes yet. I don't know what it is you're doing. Hairbands all day. Baji's not behind me yet. But yes, thank you. So they thought that the elementary particles, there's your bloody like. Oh gosh. Okay. Goodness. I thought Quark was a Ferengi bartender. Steven, do you know the word Ferengi? Wow, Steven, I'm shook. I am shook. I don't use stoves. Steven, I'm shook. I am shook with your knowledge of the word Ferengi. Give you a like when you accept my friend request. Excuse me. You know what? Your job is to come to the live, like the live, mod, sit quietly, ask only good questions, and that's it. That's all. Yes, your job. As a mod, that's the job. And say all good things about the live and constantly ask people to like it. See, Doro does it. He's like, can you please like the live? Can we get 20 likes? That sort of thing. We can be white tea pals. Let's end it there. Never seen Star Trek. Okay, you guys. Okay, I'm gonna read. See, you've made me laugh and talk too much. Okay. These particles were named quarks by the Caltech physicist Murray Gell-Mann. So the thing that further breaks down protons and neutrons up to about 30 years ago. It was okay. Up to about 30 years ago, it was thought that protons and neutrons were elementary particles. But experiments in which protons were collided with other protons or electrons at high speeds indicated that they were in fact made of smaller particles. These particles were named quarks by the Caltech physicist Murray Gell-Mann, who won the Nobel Prize in 1969 for his work on them. The origin of the name is an enigmatic quotation from James Joyce. 3 quarks for master mark. 3 quarks. Oh, very nice. Thank you for liking the live. Can we get 20 likes? I see 11. Ooh, 11. Thank you so much. Thank you. I need 20. Why? She rejected my friend request. My Cisco lol. How many likes does she need? 20. At least 20. I never knew how much fun it is in here at the beginning. We used to be stream pals, now you've betrayed me. Doro is betrayed that you are sending friend requests outside of YouTube. He wants to be your only best friend, stream related. It's you and Doro, Reese. It's you and Doro. Together forever. That's what he means. I can't believe that I have to translate this for you. Okay. The origin of the name is an enigmatic quotation from James Joyce. The origin of the name quark, that is. I don't respond to any friend requests, actually. Facebook is a mess. I have so many on there that I especially don't respond to my relatives who send friend requests because my Facebook is not that personal. It's a public platform. So you're not the only one that's getting ignored, Reese. Everybody is ignored on Facebook. Everybody. I have an account called Painbringer. Painbringer? I'll find and add you. Do you do WhatsApp? Painbringer where? Facebook? I do WhatsApp, although it's not currently on my current phone because my phone is new and I'm very, very rarely on Facebook anymore myself, and I have an account. See, Steven gets me. Steven gets it. Steven is also not using Facebook. Thank you, Steven. Thank you. Okay. 3 quarks for master mark. The word quark is supposed to be pronounced like quart, but with a K at the end instead of a T, but is usually pronounced to rhyme with lark. There are a number of different varieties of quarks. There are 6 flavors, which we call up, down, strange, charmed, bottom, and top. Those are the 6 flavors of quarks. Did you hear me? Up, down, strange, charmed, bottom, and top. I hope that Stephen Hawking will tell me the naming, what the naming means and all that, and I will tell you. So, the first three flavors had been known since the 1960s, but the charmed quark was discovered only in 1974, the bottom in 1977, and the top in 1995. Each flavor comes in three colors. Each flavor comes in three colors: red, green, and blue. It should be emphasized that these terms are just labels. Quarks are much smaller than the wavelength of visible light, and so do not have any color in the normal sense. It is just that modern physicists seem to have more imaginative ways of naming new particles and phenomena. They no longer restrict themselves to Greek. So things can be bottom and top and strange and charmed and up and down. A proton or neutron is made up of three quarks, one of each color. A proton contains two up quarks and one down quark. Two ups and one down. UUD, like combat sports said earlier, up, up, and down is a proton. A neutron contains two down and one up. So down, down, and up quark, three of those in the neutron. Down, down, and one up. We can create particles made up of the other quarks, which are, of course, strange, charmed, bottom, and top. But these all have a much greater mass and decay very rapidly into protons and neutrons. So sometimes heavier particles will decay into lighter particles. So even though they exist sometimes, even if they're natural and do exist in nature, you might not see them as often because they're decaying into the lighter counterparts. Hello, Rose. Hello, Reese. Hello, Rose. Hello, Doro. Hello, John Foster. John Foster says I can't. Can't what? You're made of the charmed quarks, unlike us. It's true. I'm made of charming quarks. You guys are made of Star Trek or something. And Reese is a bottom quark. Okay. I'll add Reese for the lols. Add John Foster too. He's in the gang. Rest assured, I'll never add you on stuff we can't break the barrier. Thank you, Doro Madness. See, Doro Madness really gets it. He's like extremely compartmentalized. He's a mod on YouTube and that's it. He keeps his quarks separate. Add John Foster. So were you serious when you said that you have an account called Pain Bringer? Pain Bringer? That's quite something. But look at you guys. Sounds like TV. Oh, you guys are talking about your brothers and stuff now. Okay, great. Very nice. Which I haven't seen. What have I not seen? Memes? I see memes. I exchange reels with some people. I like the tiara. It's a hairband, but thank you. I exchange reels with a few of my friends. They're probably gonna. I send them too many reels though, so they'll probably delete me any day now. We now know that neither the atoms nor the protons and neutrons within them are indivisible. Super chord theory, superstring, you mean? I'm not sure. I'm not sure. Let's see what Stephen Hawking says about that. That's a good question. So the question is, what are the truly elementary particles, the basic building blocks from which everything is made? Since the wavelength of light is much larger than the size of an atom, we cannot hope to look at the parts of an atom in the ordinary way. We need to use something with a much smaller wavelength. As we saw in the last chapter, quantum mechanics tells us that all particles are in fact waves, and that the higher the energy of a particle, the smaller the wavelength of the corresponding wave, because higher the energy means higher the frequency means smaller the wavelength. So the best answer we can give to our question depends on how high a particle energy we have at our disposal, because this determines how small a length scale we can look. These particle energies are usually measured in units called electron volts. So if you haven't heard about this particular unit of energy, now is the time. There is another unit of energy called electron volts. In Thomson's experiments, J.J. Thomson, remember the electron guy, with electrons, we saw that he used an electric field to accelerate the electrons. So that's what he was kind of doing to do stuff with the electrons. The energy that an electron gains from an electric field of 1 volt is what is known as an electron volt. Sometimes we say electron volt or EV as the energy unit. George Washington's breakfast. In the 19th century, when the only particle energies that people knew how to use were the low energies of a few electron volts generated by chemical reactions, such as burning, it was thought that atoms were the smallest unit. In Rutherford's experiment, the alpha particles had energies of millions of electron volts. More recently, we have learned how to use electromagnetic fields to give particles energies of at first millions and then thousands of millions of electron volts. And so we know that particles that were thought to be elementary 30 years ago are in fact made up of smaller particles. I'm dropping out of Everest. What do you mean? Are you going to the Everest and then doing skydiving? Might change mine to Kamala's cackle. Do it. So once again, in Rutherford's experiment, the alpha particles had energies of millions of electron volts, so quite high. More recently, we have learned how to use electromagnetic fields to give particles energies of at first millions and then thousands of millions of electron volts. So lots and lots of electron volt energy. And so we know that particles that were thought to be elementary 30 years ago are in fact made up of smaller particles. So if we're going to smash together things at higher energies, sometimes we discover new particles and we realize that, oh my gosh, actually this particle is made up of even smaller particles. For example, the proton is made up of 3 different types of quarks, and the neutron is also made up of 3 different types of quarks. Down, down, up, and up, and down. In fact, let me say that again. Proton contains 2 up quarks and 1 down quark. Neutron contains 2 down and 1 up. And there's also the other types of quarks, strange, charm, top, and bottom, that are less sort of common because they are heavier and they decay into the lighter types. Okay? So, may these, as we go to still higher energies in turn, be found to be made from still smaller particles. So you might ask, at what point do the divisibility kind of end, and do we have the smallest type of particle or not, right? Or do these things break down even further into even smaller particles? That is a great question. If you're wondering, many have wondered that. Thank you for liking the live. Can we get 20 likes? So this is certainly possible, the thing about breaking down into further smaller particles, but we do have some theoretical reasons for believing that we have or are very near to a knowledge of the ultimate building blocks of nature. Using the wave-particle duality discussed in the last chapter, everything in the universe, including light and gravity, can be described in terms of particles. These particles have a property called spin. So we actually mentioned a particle property called spin a while ago. Thank you for liking the live. Can we get 20 likes? Domain expansion Gojo. Hi, please say hi. Remember me, I'm Ian. Ian, how are you? Ian, how are you doing? Tonight? Hello, Ian. Thank you so much. Please do like the live. And if you have, thank you so much. Can we get 20 likes? Thank you, thank you, thank you. So, further breaking down into even smaller particles is certainly possible, but we do have some theoretical reasons for believing that we have or are very near to a knowledge of the ultimate building blocks of nature, which is basically this lepton, quark, and boson story that I started the live with. Using the wave-particle duality discussed in the last chapter, because remember we talked about wave-particle duality of both light as well as matter, everything in the universe, including light and gravity, can be described in terms of particles, where light, the particle nature of light, is called photons. I don't know that we know that much about the particle nature of gravity, but we will see what he says. These particles have a property called spin. One way of thinking of spin is to imagine the particles as little tops spinning about an axis. However, this can be very misleading. I actually don't like that particular analogy, but let's see what Stephen Hawking wants us to know here. So this whole top spinning about an axis, that's misleading because quantum mechanics tells us that the particles do not have any well-defined axis. What the spin of a particle really tells us is what the particle looks like from different directions. Hello, Ian. Don't worry. I'm reading, but I'm very happy that you're here. Please do like the live and stay on. Don't worry about being ignored. You are much loved. Thank you, darling. Thank you for being here. What the spin of a particle really tells us is what the particle looks like from different directions. A particle of spin 0 is like a dot. It looks the same from every direction. This is kind of helpful, actually. On the other hand, a particle of spin 1 is like an arrow. It looks different from different directions. Only if one turns it around a complete revolution, 360 degrees like, does the particle look the same. A particle of spin 2 is like a double-headed arrow. It looks the same if one turns it around a half a revolution. Again, a particle of spin 2 is like a double-headed arrow. It looks the same if one turns it around half a revolution. Similarly, higher spin particles look the same if one turns them through smaller fractions of a complete revolution. All this seems fairly straightforward, but the remarkable fact is that there are particles that do not look the same if one turns them through just one revolution. You have to turn them through 2 complete revolutions. Such particles are said to have spin 1/2. Wow. Ian is from even older days, Doro. I do remember Ian. Thank you, John Foster. She does do thirsty trap videos? What do you mean? Which ones? Which ones are trap? Check TikTok? What do you mean? Okay, I'm about to show you. Hi, Wade. Hello, Wade. Can you please like the live? Can we get 20 likes? Thank you. Thank you, Chickpea Break. I mean, I think women want money. That's true, but I don't know about just that money. Let's lose a pack of million. Hello, Ian, again. Okay, this is very, very important. Very, very important. Listen to this. This is actually fairly good explanation of spin. I am glad about Stephen Hawking doing that. So, the remarkable fact is that not all particles, there are particles that do not look the same if one turns them through just one revolution. You have to turn them through 2 complete revolutions. Such particles are said to have spin 1/2. So once again, a particle of spin 1 is like an arrow. It looks different from different directions. Only if one turns it around a complete revolution does the particle look the same. Okay. A particle of spin 2 is like a double-headed arrow. It looks the same if one turns it around half a revolution. Similarly, higher spin particles look the same if one turns them through smaller fractions of a complete revolution. Aha! All this seems fairly straightforward, but the remarkable fact is that there are particles that do not look the same if one turns them through just one revolution. You have to turn them through 2 complete revolutions, and these are the spin 1/2. Aha! Fermions have spin 1/2. I need that PFP. What is PFP? What do you mean? Screenshot of low resolution phase of entry. Okay, here, I'm ready. Screenshot right now. Go ahead. Screenshot. Do you got it? Okay, I'm going to show you a picture really soon, but I want to keep going for now. All the known particles in the universe can be divided into 2 groups. Particles of spin 1/2, which make up the matter in the universe, and particles of spin 0, 1, and 2, which, as we shall see, give rise to forces between the matter particles. 1 second. She's sending a reel. Oh, shut up. I'm not. Okay. So, what did we just learn? We learned a very important thing right now. It is 12:02 in the morning. All the known particles in the universe can be divided into 2 categories. Either they have a spin of 1/2 and make up all of the matter in the universe, or they have a spin of 0, 1, or 2 and make up the forces of nature, the fundamental forces of nature, the forces that these matter particles use to interact with each other. So we will keep going. The matter particles obey what is called Pauli's exclusion principle. This was discovered in 1925 by an Austrian physicist, Wolfgang Pauli, for which he received the Nobel Prize in 1945. He was the archetypal theoretical physicist. It was said of him that even his presence in the same town would make experiments go wrong. Pauli's exclusion principle says that 2 similar particles cannot exist in the same state. That is, they cannot have both the same position and the same velocity within the limits given by the uncertainty principle. The exclusion principle is crucial because it explains why matter particles do not collapse to a state of very high density under the influence of the forces produced by the particles of spin 0, 1, and 2. A free education. Yes, indeed. If the matter particles have very nearly the same positions, they must have different velocities, which means that they will not stay in the same position for long, right? Because we also have the uncertainty principle. If the world had been created without the exclusion principle, quarks would not form separate, well-defined protons and neutrons. So this is Pauli's exclusion principle. Once again, if the world had been created without the exclusion principle, quarks would not form separate, well-defined protons and neutrons. Did you got it? Gosh. Nor would these, together with electrons, form separate, well-defined atoms. They would all collapse to form a roughly uniform, dense soup. I can't even tell the difference. I guess my face looks different in that one. So we could have been a roughly uniform, dense soup, but because of the exclusion principle, we've got all these separate things, well-defined atoms, electrons, separate well-defined atoms. A proper understanding of the electron and the other spin 1/2 particles did not come until 1928. So pretty much what we learned is the particles that have spin 1/2 basically make up all of matter. Electrons, protons, neutrons, well, basically the quarks that are inside of the protons and neutrons. These things have spin 1/2. Or sorry, actually I got that wrong. Protons and neutrons, quarks have a different spin. The protons and neutrons together, I believe, have the spin 1/2 actually. Yes. Neutron degeneracy pressure, spin 1/2. Yes. Sorry, that one was wrong. All of the particles that make up matter, like electrons, protons, neutrons, have a spin of 1/2. All of the particles that make up the forces between such things, or just the forces of nature, have spin of either 0, 1, or 2. Quarks actually have a slightly different kind of spin. We will talk about that. Do you like Subway? Random question. I like the Subway as in the train under the ground. I do like that. I don't much eat Subway sandwiches. I will soon delete them. Internet, I don't even know at this point who Water Break is. So if you have my picture on your phone, I mean, I don't know who you are. I think that's Doro. I can't tell. There's too many of my aliases now. Subway sandwich, I mean, I'm willing to eat one. I just usually don't. I think Water Break is Dora, but there's more now. I think I've been seeing a couple more. So I don't know. I think that's him. I don't know. I don't know. So let me keep going. Did a date buy you one? No, never. I think my parents have bought me some Subway sandwiches, to be totally honest. I think it's more likely that my dad bought me a Subway sandwich and I might not have been having the best day or something during such a whatever. So, and I think that Subways are always owned by Indians, right? Andre's Water Break is the OG Owens. Thank you. Subway loved me when others didn't. I'll always love Subway. Actually, I have nothing against Subway. If somebody wanted to take me to Subway and bought the sandwich, that would be fine, probably. In fact, I kind of want a sandwich now. Subways are always owned by Indians, yeah. I believe that more Subways are owned by Indian people than they are not. Yeah, I don't own one, but that's what I read somewhere. It could be true, it could be not true. Want Subway as a date night event? No, I don't. Mm-mm. I do not want Subway on a date. No. I think me eating a very big sandwich could be daunting for the date. I feel like a hole. Like a hole? Like a HOLE hole? I want chickpeas. Yes, I would rather do chickpeas. Thank you so much for liking the live. Can we get 20 likes? Thank you so much for being here. Okay, so a proper understanding of the electron and other spin 1/2 particles did not come until 1928, when a theory was proposed by Paul Dirac. I feel bad now. For what? Dismantle your microwave? What? A proper understanding of the electron and other spin 1/2 particles did not come until 1928, when a theory was proposed by Paul Dirac, who later was elected to the Lucasian Professorship of Mathematics at Cambridge, the same professorship that Newton once held and that I now hold. So Stephen Hawking had this position, Lucasian Professorship of Mathematics at Cambridge. Dirac's theory was the first of its kind that was consistent with both quantum mechanics and the special theory of relativity. So actually, Dirac, remember, wrote down the relativistic equations for the wave equation of a particle. Oh, you're fine. That's okay. I think I was just saying I was just saying that as a piece of fact, not to bring up race. The Subway owning thing. I was not commenting in a racy way. I was just saying as a piece of fact that I read somewhere. Actually, I think, yeah, he doesn't live here very much. He goes to Maine. Popeyes? What do you mean? Okay, so Dirac had turned those equations into relativistic equations. Dirac's theory was the first of its kind that was consistent with both quantum mechanics and the special theory of relativity. He basically took quantum mechanics and introduced relativity to it. He basically wrote down the relativistic equations, relativistic version of the same equations of quantum mechanics. It explained mathematically why the electron had spin 1/2, that is, why it didn't look the same if you turned it through only one complete revolution. But did if you turned it through 2 revolutions? She sang him out. Maybe. So it also predicted that the electron should have a partner, an anti-electron or positron. So now even the electron looking for a partner, and that partner is called anti-electron or positron. Can we get 20 likes? The discovery of the positron in 1932 confirmed Dirac's theory and led to his being awarded the Nobel Prize for Physics in 1933. We now know that every particle has an antiparticle with which it can annihilate. In the case of the force-carrying particles, the antiparticles are the same as the particles themselves. There could be whole anti-worlds and anti-people made of antiparticles. However, if you meet your anti-self, don't shake hands, you would both vanish in a great flash of light. The question of why there seem to be so many more particles than antiparticles around us is extremely important, and I shall return to it later in the chapter. Yay! I don't feel authentic. What do you mean? Can you not work a phone? In quantum mechanics, the forces or interactions between matter particles are all supposed to be carried by particles of integer spin. Spin, if you saw two E's there, but there's only one I, not E. So if you saw integer spin like 0, 1, or 2, then that's a force particle, or forces or interactions between matter particles. What happens is that a matter particle, such as an electron or a quark, emits a force-carrying particle. I got her with some weird faces. I now know to phone use my. You're funny, but cannot work a phone. Chickpea break. He cannot rewind. What weird face? Use this face. Here. Cleopatra face. Use this. Go ahead. Chickpea. You know, you guys, Dora's. Sorry, my laughing is so loud. Every time I laugh that much, the neighbor leaves and the people on the live also leave. Extremely sorry about the amplification of that laugh. I can use my phone. With all the water I'm drinking. Did someone just give me $2? What the frick is this? Oh, thank you. Thank you so Thank you so much, Thoughtful Coyote. Thoughtful Coyote says, bought a used gaming chair. Why is it crunchy? It's spring water or something. Sorry, I didn't even realize that somebody just gave me money. Thank you so much. Thank you, thank you, thank you. Love it. Love you. Thank you. We're most grateful. Thank you so much, Thoughtful Coyote, for $2. You have made my whole day. I will buy all my groceries with that, such as this bottled water. Thank you so much. Thank you so much. Thank you so much. No, Steven. Lol, is that spring water? Thank you once again, Thoughtful Coyote. You made my whole day. Nobody donates usually, and you have. You are great. It's so supportive. See, he's so supportive. What are the people doing? What is going on? You're an iceberg. You can pay to get me to read something. He may charge it? What? What are you saying? I'm a she. Thank you, Thoughtful Coyote. Thank you, girl. You're a she. How nice. Thank you so much. You're the best. You're the best girl I've ever met. I wish someone would make it rain on me for a change. For a change, like change of money. Thoughtful Coyote. Money well spent. What's this channel about? This is about cats and physics, Thoughtful Coyote. My full attention is not now on you. How are you? How are you? Where are you? What do you want? Tell me. Tell me. Thoughtful Coyote, she has no idea what she said. What do you mean? Oh, That's true. I was under pressure. I don't know what I said. Thank you, Thoughtful Coyote. This channel is about kitty cats and physics and astronomy and cosmology. How are you, ma'am? I kind of just rolled in and landed here close to... I like the way you dance. What do you mean? A spazzed on gaming chair? Okay. So, in quantum mechanics, the forces or interactions between matter particles are all supposed to be carried by particles of integer spin 0, 1, or 2. What happens is that a matter particle, such as an electron or a quark, emits a force-carrying particle. The recoil from this emission changes the velocity of the matter particle. The force-carrying particle then collides with another matter particle and is absorbed. This collision changes the velocity of the second particle, just as if there had been a force between the two matter particles. It is an important property of the force-carrying particles that they do not obey the exclusion principle. Oindri does love guys a lot. She enjoys what made the chair crunchy. I don't know what that means. Hates men. Okay. I was crying laughing. You danced last week with the honey wine in your system. I don't know what is going on, but you guys are off the charts today. Thank you so much. Thank you so much. Okay. Girl, it's $2. Why would I care? Thoughtful Coyote, it's not just $2 for me. It is encouragement. It means a lot to me. It means everything. The world. The whole world is in those $2 right now, Thoughtful Coyote. I didn't even know whether supers worked or not because nobody frickin'... Thank you so much. It means the world to me to have your encouragement and support. Can we get 20 likes? Can we get 20 likes? We are 4 short. What would you do for 10? Make the 10 happen, John Foster, before you ask such hypothetical questions. Only super chat she ever gets is a hilarious troll. Just kidding. You're kidding? Gosh. At least make a fake alias of me. Don't just kid. It's either the $10 or you have to make a fake account. I would buy a month worth of chickpeas with $10. Exactly. 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 Do you drop bombs like that in the chats normally? What? Hold on what? Hold on what? Do you want me to pose? My... You'll give me 2 slave owner dollars? Do it. Why is it called slave owner? Do it. I need proof that supers are actually working, and Thoughtful Coyote, by the way, I love the username Thoughtful Coyote. Prove to me that these freaking supers even work. John. Did it happen? I can't tell. Suddenly there was this other type of chat looking thing. Coyote, you made my day. You made my night. In fact, you made my whole life with the encouraging donation. That was so funny. Yeah. They were slave owners technically, lol. Who? Oh! Who? Your troll message was encouraging. Yes, of course, it was. Okay. So I'll keep going for a second. The recoil, what happens is that a matter particle, such as an electron or a quark, emits a force-carrying particle. The recoil from this emission changes the velocity of the matter particle. The force-carrying particle then collides with another matter particle and is absorbed. This collision changes the velocity of the second particle, just as if there had been a force between the two matter particles. It is an important property of the force-carrying particles that they do not obey the exclusion principle. This means that there is no limit. This means that there is no limit to the number that can be exchanged, and so they can give rise to a strong force. However, if the force-carrying particles have a high mass, it will be difficult to produce and exchange them over a large distance. So the forces that they carry will only have a short range. On the other hand, if the force-carrying particles have no mass of their own, the forces will be long range. The force-carrying particles exchanged between matter particles are said to be virtual particles because, unlike real particles, they cannot be directly detected by a particle detector. We know they exist, however, because they do have a measurable effect, they give rise to forces between matter particles. Thank you for liking the live. Can we get 20 likes? There is a lot of me on the screen. Yes, thank you, thank you, thank you, thank you. Particles of spin 0, 1, or 2 do also exist in some circumstances as real particles when they can be directly detected. When they can be directly detected, then they're more real. Then they appear to us as what a classical physicist would call waves, such as waves of light or gravitational waves. So by the way, Reese, this is sort of related to the question you asked about wave-particle duality. So when a particle with spin 0, 1, or 2, thank you. What happened? I will be her slave, Abraham Lincoln. Oh, do you work for Abraham Lincoln? That's right. Lincoln was an interesting person with a very nice library, I will say. I've seen his library in a museum. Or do you take food stamps? What does that even mean? Waves on the Titanic. Let's try the super chat, guys. Yes, John Foster. The super chat is open for you to try out. I'm not sure it works and I need some chickpeas. That's correct. Wait, is chickpea ver? Ver, did you figure it out? Oh my gosh. No. I think that's Doro. What's a super chat? Oh my god. After all this drama, now you're asking what a super chat is? You're Ver? Oh, look at you, Ver. Look at you. Thank you. Okay. So we know they exist, however, because they do have a measurable effect. They give rise to forces between matter particles. Particles of spin 0, 1, or 2 do also exist in some circumstances as real particles when they can be directly detected. Then they then appear to us as what a classical physicist would call waves, such as waves of light or gravitational waves. They may sometimes be emitted when matter particles interact with each other by exchanging virtual force-carrying particles. For example, the electric repulsive force between two electrons is due to the exchange of virtual photons which can never be directly detected, but if one electron moves past another, real photons may be given off, which we detect as light waves. Force-carrying particles can be grouped into 4 categories according to the strength of the force that they carry and the particles with which they interact. It should be emphasized that this division into 4 classes is man-made. Virtual. Yes. It is convenient for the construction of partial theories, but it may not correspond to anything deeper. Ultimately, most physicists hope to find a unified theory that will explain all 4 forces as different aspects of a single force. Indeed, many would say this is the prime goal of physics today. Recently, successful attempts have been made to unify 3 of the 4 categories of force. Yeah. And I shall describe these in this chapter, the one that we're on. The question of the unification of the remaining category, gravity, we shall leave till later. So the 3 things, there's a weak force, strong force, and electromagnetism, he will talk about sort of unifying or whatever in this exact chapter. But then gravity is sort of off on its own a little bit. I try to stay serious, but you guys do distract. I have no clue. Clue about what? Do you guys like my headband? Can we get 20 likes? Yes, 3 more likes to 20. Either you double tap and like the live or do a super chat, do something. Time to be silly. Oh, I actually do have to use the bathroom quite badly, actually. Indeed. Do something. Okay, so when I'm back from the bathroom, we will talk about the gravitational force. So in the next part of the chapter, he's going to talk about gravitational force. That is one of the force categories. There's 4 force categories: gravitation, weak force, strong force, and electromagnetic force. Turns out in the next little paragraph, he's going to talk about gravitational force. And I have to use the bathroom. It's not a water break, it's a bathroom break. You need another profile for bathroom break. Time to be silly. Do something. All of these profiles start with my name. So thank you everybody so much for being here. I have to use the bathroom real quick. The whole chat will leave after the 1.5-hour break. What? No, don't. We will finish up gravitation and the other 3 forces today for sure. When I'm done from the bathroom and a bite of chickpea, I'll talk about gravitational force. Real quick. Oh, we have quite a bit left, actually. You guys, we're not done at all. We have gravitational force to talk about. We have 3 other types of forces. W and Z bosons. Maybe we will be silly the rest of the live. Actually, I'm thinking this chapter is kind of long. Gary says, haven't seen you in ages. Hello, Gary. How are you and Baji? Baji is still not quite behind me. Gary, can you please like the live? We need 20 likes at least. If my girlfriend sees a picture of Ondri on my phone, I'll be in the shit. You should do something about that, Reese. Delete it now. I still see the shelves. Still, Yes, there's the shelves right behind me and beside me. Didn't stop you gooning. Baji's on my head. What does this even mean? If my GF sees a picture, well, hopefully she sees these pictures and the friend requests you've been sending. Reese's girlfriend, Reese's Pieces is being a bad boy. I turn on my computer's light. Oh my God. The whole chat. Okay, I really have to use the bathroom. It's bad. It's bad. I'm going to finish the water first, actually. How about we will finish up this chapter tomorrow because it's quite long. Elementary particles and the forces of nature. But the rest of the live is for fun. The rest of the live, we will just be silly. We will just be silly because there's too much silliness in the chat anyways. And I'm not sure where the focus of this is going. And Coyote, Thoughtful Coyote, once again, thank you so much for the $2. If anybody else wants to give me $200, $2,000, $20 million, now's your chance. Thank you for liking the live. We have 18 likes. Goodness. Thank you. 2 more and we will be at 20 likes. Thank you so much. Thank you. Thank you so much. Thank you very much indeed for liking the live, the whole chat. Where are the explanations of these comments? Gary, how are you? How are you doing? I think I'll go to the bathroom too. I don't have a picture of you. I meant if I was to make an alt like Doro. Oh, you didn't make an alt yet? Oh. Did someone? What? Gary gave me $1.99. Oh my goodness. Wow. Gary, thank you so much. Goodness gracious me. Somebody else gave me a super. Coyote, I'll let you know. I'll let you use my stove to cook. I only use microwave. What? Let's celebrate. How do I do this? How do I like the super chat? Thank you so much, Gary. Thank you so much. Really appreciate it, but I don't know how to like it. How do I like it? It's showing up on the chat. Let's celebrate their first super on a live stream. Oh my gosh. Oh, Gary, it's your first super chat on a live. Oh, it's Gary's first super chat on a live stream. Oh my God, Gary, congratulations and congratulations to me. So lucky to have you here today. That's dope. Thank you, Thoughtful Coyote. Thoughtful Coyote and Gary have made my entire day. I'd say my gooning is pretty mild. You would have to make me a lot of dinners for that amount. What? For the $3.99 or the 20 million? I do like her personality, though. She's funny. Oh, your girlfriend is funny? Aw, tell us more. I don't know how donating works. My actual first time. Yes, you just did it. Gary just did it for a super chat. Gary just did a super chat. Gary, can Kay marry you? Who is Kay? Who's Gary? Gary is right here. He did a super chat and he's saying that it's his first time. So yeah, you can donate with the super chats. And you just did it. It worked, I think. I can see it right there. And also I see it in the chat. It became a blue highlighted chat. I'm Gary from New Jersey. Look at New Jersey. Most welcome. Most welcome. I was born at a young age. I'm qualified to be your wife. Goodness, that's quite a comment from Thoughtful Coyote. Doro, stop it. My girlfriend is pretty funny, says Reese. Principles is she is a sweet woman with a cool cat and great knowledge. I have actually multiple cool cats. Thank you so much. I'm rich and I have a lifetime supply of chickpeas, says my alt account, chickpea break, which is actually Ver. I'm gonna give you Really? Water break is gonna give me $3.99. Wow. Do it. Water break. See, this water costs me. I could buy this water with that. How do I see notifications of you when you go live? Thoughtful Coyote. So I think you subscribe to me and maybe have to press the bell icon or something. I think so. So yes, please do like, share, subscribe, everybody. And Gary, thank you so much for the super chat. And I believe what you do is you like the live generally. You subscribe to my channel, and then you might have to click on the bell icon for it to become giving you notifications, for it to give you notifications when I have gone live. And I've been going live pretty much on the weekdays every night. So I think I haven't seen you in a while. So yes, indeed. No, who is saying no? Don't ever stop, Coyote. To what? Yes, sub and bell icon. Thank you. Somebody has said something useful, which is that you subscribe and then hit the bell icon. Thank you. I really just did it there. Oh, good. Gary just did it. Many thanks. Thank you. Thank you, thank you, thank you. Now you are subscribed and hopefully you'll get the notifications. Thank you, thank you, thank you. I do have to use the bathroom, guys. I'll be right back. I'm literally amazed. Okay. I will keep out of that the marriage discussions. Thank you. Thank you. Thank you. Thank you. So today we can continue to chat. I have to use the bathroom. And we will finish up elementary particles. We kind of got into the elementary particles and the forces, the fundamental forces of nature, and how really this property called spin is affecting sort of our experience of these particles, and also how they interact and blah, blah, blah. Turns out the spin 1/2 particles are pretty much what make up all of the matter, like electrons, protons, neutrons. And then spin 0 or 1 or 2 make up generally the types of particles that are really the force carriers. So anytime two particles interact, they're exchanging some carrier particle, which is really a type of force. It could be one of the 4 fundamental forces of nature that we talk about here. And that force particle is also a type of particle, generally called a boson. And it will have a spin of either 0, 1, or 2. And depending on which spin, of course, it's going to be a different type of boson. So that's kind of what we looked at today. There is more details. I realized that this chapter is a little bit dense in information. There's quite a lot that's going on. We're kind of getting a review of like the standard model of particle physics in this chapter. So I don't want to burden you with too much at once, but it is a very important chapter, and we will recap it. We will review it. We might have to finish it tomorrow, but when I'm back, definitely we will continue. It might be that we just chat casually the rest of the night tonight and pick it up tomorrow for the particle physics. Amazing how someone so young knows quantum mechanics or physics. I'm not that young, and I did go to school for it. Thank you so much, Gary. Thank you. I did go to school for physics. I had to take many years of not many years. I took a year of quantum in undergrad and another year in grad school, and we all cried. Lots of tears were rolling down our cheeks when we took quantum in grad school. It was very difficult in grad school indeed. Gary, I can learn particle physics for you. Thoughtful Coyote, that's a very thoughtful thought you should learn quantum mechanics and particle physics, I think it will that will be great, and you should keep coming back to my channel to do that. We will together learn quantum mechanics and particle physics. I think you can definitely learn a lot from the channel. Be back here tomorrow, same time. I do have to go to the bathroom. Is Coyote a him? But Coyote said it's a she, so I believe it. Believe her. Okay, Doro and Reese and everybody, can you please keep the chat entertaining? I really gotta take a pee-pee. Can you please, please, please keep the chat entertaining? I don't want everybody to leave. Okay, I really gotta pee. Okay, I'll be right back. Just 1 second. 1 second, please. it's a little, it's a little cold. I'm back already. I really did just have to pee. Maybe I'll eat chickpeas now. Hi, Mohit. What do you mean? Reese, you're being very explicit. Can we get 20 likes? Thank you so much. Thank you so much for liking the live. Can we get 20 likes? It's fun to stay at the... Change your name. I'm back! You guys! Gosh! Sometimes I do come back, you know. Sometimes I come back. You guys don't even know because you've left already. Because a poor girl had to pee. Sometimes I come back. And you guys just wouldn't even know because you've left already. Because you think that I have not come back when I actually have. You just don't know. You don't know things. Can we get 20 likes? My lips are dry. Dora Madness, don't listen to him. He doesn't know how to check the time. Dora Madness doesn't know what time it is. Hi Varun, hi John Foster, hello Dora Madness, hello John, hello Varun, hello Chickpea Break. Actually, I'm kind of hungry. Should I make some chickpeas, guys? Should I? Why did the atom lose its jobs? Because it couldn't bond with its co-workers. Aww. I'm gonna keep coming back to these streams because I know Gary will come back eventually. Oh, did Gary leave? Oh. Did Gary leave? Oh no! Gary, are you here? I'm back. You can ask me a quantum mechanics question. Yes, Coyote. Hide her microwave. She's hungry. I only use the microwave. That's true. I do. A good chole masala would be tasty. See, Varun Malik agrees with my chickpea eating. It's chickpea, not chicken pea. I'm gonna eat chickpeas now, guys. You can't stop me. Should I eat cereal? I think I want some chickpeas. Should I make cup noodle? I have a cup noodle. Wait, 1 second. Don't go anywhere. I'll be right here. I have a cup noodle. See, my good friend gave me this, knowing fully well that this is the extent of my cooking. Overwhelming nutritional choice. Exactly. I want some chicken tikka. Oh, Gary, do you want more quantum mechanics conversations? Are you guys harassing Gary? How cordial. Okay, let's see how this works. Microwave directions. Remove lid. Add room temperature water. . Place in microwave center. This is too complicated. Microwave uncovered for 4 minutes. Stir and enjoy. Oh my God, it's amazing. It smells great. Oh, oh yes. This is called sweet chili flavor stir fry style Asian noodles in sauce. In sauce. I almost want to cook food. I almost want to cook you food. Thank you. Looks spicy Korean. I think my friend got this from Singapore. Let's see. Manufactured in a facility that also processes egg, milk, peanut, tree nuts, crustacean, shellfish, and fish products. This is, does it say made in where? I think it's made in California. Ooh, it says vegetarian. Basically Coyote loves Gary and we want the best for Coyote. Gary, I cannot cook with a stove. What do you mean? See, Gary likes my content. Gary likes physics. Gary likes cats and physics. Gary likes cats and quantum mechanics is why he donated. And then you guys made fun or something and now Gary's gone. My one, other than Steven, Gary actually likes quantum mechanics and cats. As far as Indo-Oriental street food goes, Singaporean noodles are the best. Yes! Varun knows what's up. Varun knows what's up. I need chickpeas. That's true, I do. But I think I'll eat the noodles. Really, that's how you cook your food, just microwave? Yes, what's wrong with that? Sometimes I use the induction stove. We got 20 likes. Thank you. Thank you, guys. Thank you so much. Okay, I'm going to transfer. You'll see my cooking style right here, right now. I'm going to transfer these into a bowl. And then I will cook it in the microwave because I'm afraid that this thing will leak some kind of plastic into the food. So I will be careful and put this into a glass bowl and then cook it and then make it and then eat it right here with you. Baji does too. Yes, Baji does what? What about Ver? I love your content. Oh, thank you. Yes, Ver likes my content. Thank you, Ver. Thank you, Steven, Ver, and Gary. And the rest of you are naughty, naughty people. You actually use a stove. Yes, I have an induction stove. I cook ramen in that. I basically use it to boil water. I cook ramen in that. And I can make eggs. I make eggs sometimes. Dora says, I love your streams. Thank you. I like the content to be fair. Reese likes the content to be fair. It is true. He asks some good questions sometimes. Reese, you used to ask more physics questions a while ago. Then we fought about the moon landing. Actually, it's not even that. I think you just like the Titanic stuff more. I was here before the physics stuff. Aw, thank you, Doru. None of your past dates never cooked you food? No, they did. That's not true, actually. I will say one good thing about the dates is that they generally cooked. But the chat is hilarious now. Chickpea, I love your content. Thank you. Thank you. Okay, you're gonna hear me make this in the microwave right now. In a bowl. Yeah, they cooked because that's how they will get food too. Otherwise, they have to eat this. So yeah, they all cooked. They're all cookie. Cook types. Baji Baba. Oh my gosh, Baji Baba is over here waiting for something. supposed to add water. My friend Shruti gave me this cup of noodle. She too doesn't cook. So she understands my problems and gave me cup of noodle as a gift when she went to Singapore. My friend went to Singapore and she brought me this cup of noodle from there, knowing fully well what our struggles are in life. She too does not cook. Yay! But I have another friend who does cook, and that's how we all survive. I'm adding extra water. धीरे जलना धीरे जलना धीरे जलना. Can't understand quantum mechanics, cannot operate stoves. I'm just afraid of the gas stove. जिंदगी की आगे जलना धीरे 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 जलना. What's Baji's favorite snack? Every type of food ever, especially the ones that he can steal. Thank you for the super chats, guys. It's how we're gonna afford more Baji snacks. Thank you, thank you, thank you, my cup of noodle friend. True, my cup of noodle friend gave me the cup of noodle. Cannot operate stove, that's right. I generally do have to go to bed if Gary comes back. Thoughtful Coyote! Good night. Until tomorrow, Thoughtful Coyote, please do come back and donate more. Loved to see you today. Can I see your mom? My mom? Oh, don't worry about it. Alex is a kid. Alex Sandoval is a kid. Can I see your mom? I think this kid thinks that I am a kid too. You know what I mean? It's okay. You can maybe see my mom. She is going to visit me soon, actually. You might be able to see my mom. The gas suppliers add a smell. Oh, really? Oh, thank you. I press buttons on a microwave to sustain myself. It's less effort. Have you learned classical music? Yes, a little bit. Your sur and tal is on point. I did learn some music, yes. Thank you. Owen's mom stream. Well, I don't know if she'll agree to be on the stream, but for a liberal, you're very easy on trolls. Aw! I am very easygoing. I don't really mind too much. For a liberal. Maybe I'm not as liberal as you think. She deals with them brilliantly, to be fair. Aww! Mainly because she doesn't understand when there's a troll. Moms might have the slipper in hand during the live. Actually, guys, my mom will be coming here. She also does not like to cook. I cried. Well, if I cried about Trump, then why didn't you send a super chat? We need Baji's hissy fit for the trolls. Yes, my mother also does not cook. you guys. I mean, she'll probably cook some. We will together. We will together cook something, but we'll probably get zooby dooby pampara zuzu momo. We will get some takeout. Oh my god, the noodles are boiling. Oh my god, this is so much cooking. I've done a lot of cooking, guys. A ton. Just an amazing amount. There's a lot of cooking happening in the microwave. Wow, it smells amazing. Wow. Zooby dooby bum bum bum. We will get takeout from a restaurant when my mom is here. That will be our cooking, because once we get the takeout, we do need to reheat the takeout. Your mom doesn't cook either. Have you ever actually had a proper meal? Yes, of course I have. Yes, of course I have. She cooks a few things, but she doesn't like to cook. Do you eat meat? Do you see the smoke coming out of this? Do you see this? She looks healthy. She probably ate chickpeas since a young age. I can't grasp the concept of universe expanding, Big Bang Theory, galaxies constantly getting further apart from each other. There is more than the universe where it is expanding into. There is more than the universe. Yes, so we talked about the expanding universe a couple of lives ago. There is something of an anti-gravity force that is pushing things out and making the universe expand more and more. Now, exactly how much it's expanding, that is sort of, there's various cosmological models that can help with that. Either the expansion could happen and then slow down and we could end up in a big crunch, or there could be a lot of expansion with a very high rate, so we keep on expanding and expanding forever. Or the expansion rate could be just enough to make us expand and not collapse on itself, collapse under gravity. That is, like, basically avoids the big crunch, but doesn't keep on expanding too rapidly. So there's these different cosmological models that we talked about, and we can kind of see which one is closest to our observation of exactly what the expansion is doing and kind of check. But yeah, the term for like the cause of this expansion, we call it dark energy. It's a research topic. We don't fully understand it, but yeah, it is true that the universe is constantly, or as we know it right now, it is expanding, and it's been expanding for a while, and we expect it to keep on expanding for quite some time. Your mom doesn't cook either. I have had it. So she can cook a few things, but she wasn't a very good cook when I was growing up. She did learn to cook more after she kind of approached retirement. I guess she's more retired now and she can cook a few things, but it's not her preference to cook. So she will probably make a couple things and I'll help her, but then we'll probably get takeout. And yes, my dad can cook a lot more than her. He can cook and he can make meats and stuff. So when I meet my dad, there is usually some kind of protein available. Otherwise, I just eat the chickpeas. Reheat the takeout. Cooking mission completed. Exactly. I see just noodles. Andre is the best. Oh, yay! Thank you. Thank you. Even Deadpool likes Batman. What do you mean? Okay, yeah. Here are my noodles. You just see noodles? What do you mean? I am eating noodles. Dang, I would have liked to meet your dad. He likes to cook meats. I don't know how often he cooks meats. Like, both of them didn't really cook that much when we were young. Me and my brother. Ha! Ah! Ha! Okay, it's very hot. Um, thank you, thank you, thank you. Are your parents clever too? I think so, yeah, they're pretty clever. This is very hot. Guys, I've cooked a lot. This is very, very hot. I think a lot of cooking has been accomplished right here, right now. Who's broke and who's cute? This is a cup of noodle from Singapore. My friend brought it as a gift for me. Temporary backup. Hello, temporary backup. Number 1, you're pretty. Number 2, if universe is expanding. Is that why we're fat? That's a great point. The expansion of the universe is felt at large scales. So something in physics to keep in mind is that the scales that you speak of matter a lot. So at the scale of the Earth solar system, we are under gravitation and we're not actually expanding. The expansion of the universe is observed for larger scales. So when you look at galaxies far, far away, those galaxies are redshifted. They're moving away from us because of the expansion of the universe. But at a shorter scale, we feel gravitation more, and we would not be, like, gravitation is going to pull us together. So your question is very good, but keep in mind about the scales that are involved. At a short scale, if you have gravitation, if you have the Earth, the Sun, the planets, we're more feeling gravitation, which pulls things together. It's an attractive force. But if you go farther out and look at far, far away other galaxies, then those are going to be getting pushed farther and farther out because of the expansion of the universe. Where space itself is kind of stretching out, the distances between us and those galaxies are stretching out because of expansion of the universe. Thank you for the excellent question and comment. Temporary backup. Oh, this is most excellent. It's so tasty. This is most excellent. Most excellent indeed. I'm about to have chickpeas and go to bed. Okay. Chickpea break. Bye, chickpea break. Bye, Ver. Bye, Doro. Bye, Ver. Bye, Doro. Thank you so much. This is quite nice. Centrifugal force. If gravity is weak enough for bees and flies to overcome. Bees and flies to overcome. Have fun, chickpea. Good night. Grimmy. Are you typing out nuggets? Okay. So Let me look at that again, the question. Affect the Earth's... I need to think about that. How come the centrifugal force, so the Earth's rotation, not wait. One second. Not size of the object, but the scales of distance between us. I meant, by scale, I mean the distances in the universe. In the distance scale of the solar system, we are under attractive force of gravitation. In the distance scale of galaxies far, far away, we see the expansion of the universe. And yes, there will be less gravitation when they get farther apart. Yeah, exactly. It's an anti-gravity force, dark energy. Indeed. Oh! Oh, whoops. I too much wind coming out of my mouth. I'm still pondering the question. Let me think about that more. I don't think the centripetal, the Earth's rotation, basically you're asking, why isn't gravity different? And depending on how far you are from the center of mass of the massive body, gravity is different. It might just not be noticeable, but I don't think that the Earth's rotation would affect anything, because gravitation is just, big gravitational constant G times the mass times the other mass over r squared. It has nothing to do with the rotation, really. But yeah, the distribution of mass may change because of the rotation. Is that what you're asking about, distribution of mass? Yes, the Earth is a little bit flattened. It's not completely a perfect sphere. The distribution. Ooh, you're asking about like the moment of inertia. Yes, there is the angular momentum that is different. That is affected. I can talk more about dark energy tomorrow if you want. That sounds good. Scientists have measured expanding distances between objects in space. Yes, expanded, exactly. Scientists have measured expanding distances between objects in space. Tomorrow you will talk more about anti-gravity. I can talk more about dark energy tomorrow if you would like. That sounds good. The universe is infinite. And there is expansion, yes. Mm-hmm. 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 But yeah. Because of Earth's rotation, so Earth has an angular momentum. So the distribution of Earth's mass is affected by its rotation. Use a form of anti-gravity in order to float along on the breeze. They become statically charged, which repels the charge of the Earth. Ooh. Wow. Goodness. That's cool. That is cool. This noodle has been most excellent. So it sounds like oh wow. Oh, that's cool. Thank you for sharing, Reese. It sounds like we will continue elementary particles tomorrow night. And we will, yeah, we will continue elementary particles. And we can talk more about dark energy. Yes, my background is in physics, yeah. I'm not studying currently. I've already finished my PhD in physics. But yes, you should come to the lives and bring all your questions. Sounds perfect. Sounds amazing. Thank you. Thank you, thank you. Thank you, everybody, for coming to the live. This noodle was excellent. No. I just worked at MIT. I did not graduate from MIT. Thank you for sharing your knowledge to the world, to everyday people. Of course. Thank you. Thank you for coming to the live. I did not graduate from MIT. I graduated from NC State University and Ohio State University. I worked at a lab of MIT though. So I didn't pay MIT. They paid me. Their tuition was too expensive. So when I came to the US, we could not afford the tuition of MIT. So I did not go there. I went to NC State. I did work for a NASA project, yes. Maybe you will see my mom next week. She's coming, or she said she's coming. No, I didn't start college at 12 years old. No. I started college at 18. I wish though. I think college would have suited me better than grade school. Or grade school was fine, but I think I was ready for more seriousness earlier. I saw her. I saw her in North Carolina. She lives there. So I guess I saw her last month. Kind of recent. Kind of recent. Oops. Kinda sorta recently. Okay, let me get rid of the bowl. I'll be right back. Give me 1 second. Still have to wrap up the. Still have to wrap up the kitchen and whatnot. So give me 1 second. I think I just... Oh no, did I miss you? When did you last see your mom? I think I saw that already. Oh, my eyebrow looks weird. I think I just figured out why YouTube recommended channel. Anyway, good night to you and everyone else. Temporary backup, you're gonna keep us in a suspense. We don't know why it was recommended to you. Why was it recommended? Why, oh why? It's getting light here. What time is it there? Like yeah, it's 1:33 a.m. Still not as late as I've stayed up sometimes to do the lives, but if you have to good night, then we get it. Good night, sleep tight all. Tomorrow we're going to talk about the rest of the elementary particles, and then we will talk about there seems to be a request or a demand for dark energy conversations, so I think we'll keep that going as well. You went through college at light speeds and experienced time contraction. There is not a way you're biologically older than 26. Ah, Acacio, well, thank you. Biologically older. You know, I don't feel much older than 12 or 13 most of the time. Maybe 16, maybe 21. But age is just a number. Reese says good night. Good night, Reese. Good night to your girlfriend. Congratulations on that, by the way. Didn't know you had a new girlfriend. Congrats to my mod in Britain. Anybody else want to say good night? And then we will sign off. I want to stay and say good night to everybody. And thank you so much for all your support tonight. Tonight has been most excellent. I got 2 super chats. Most excellent. And we talked about elementary particles from the book Brief History of Time by Stephen Hawking. And we talked about spin. Spin is normally quite a confusing topic. So I'm glad we talked about it in some detail today. We will pick it up tomorrow night. We will. And here is my Baji Baba. Baji. And we will finish with Baji Baba in my lap. 1 second, guys. 1 second. Baji. Here is Baji. Baji, say hi. Here is Baji. Baji, say hi. Baji, say hi. Oh. Oh, Baji says hi. Oh my gosh, I'm sorry, Baji. Did I disturb you? Come, Baji. Oh, Baji doesn't want to hang out. Baji doesn't want me picking him up. Baji is very picky right now. Baji feels introverted. Baji doesn't want to be picked up. Oh, Baji. I totally believe you. Thank you. Thank you. Good night, Acacio. Baj is a ledge. Baj is a legend, you mean? Aww. Reese. Do you see Baji right there? Baji Baba. Baji's right there. Baji. Baji, what's wrong? Acacio, I totally believe you. Good night. Good night, Acacio. Baji's a legend. Baji. Baji. Baji, Mama's right here. Do you want to come on Mama's lap? Do you want to come to Mama's lap? Oh, Baji! Baji, Mama loves you! Baji, oh no, Baji's stuck. Baji, Mama loves you. Baji, Mama loves you. Baji, Mama loves you. Oh, Baji, do you want a treat too? I think Baji wants a treat too. Baji wants a treaty. Baji, do you want a treaty? Baji. Here, Baji. Here, you can have a treat too. Come, Baji. Come, Baji, come. Sachi. Sachi, Mama. Fuji. Fuji, Suji, Baji. Okay, they all got treats. They all got treats. They won. I think Baji has basically became the ambassador for the treats to be happening. So they all got treats, and Fuji and Suji came down. They had already retired. They don't believe in working so late. But Baji ambassadored the treat distribution right here, right now. So, good job, Baji. Baji is supposed to be on a sort of diet though, because, yeah, you know why. But it is hard to resist giving him treats. He deserves a treat, yes. He does eat more than his fair share of treats, which would explain the asymmetry in mass distribution between Baji and Suji, for example. But he was crying for some Doritos, so he just got some. They all got some, but Baji got some too. Of course, because he's such a sweeto. They all are. I don't like when he eats Suji's food though. I have to give Suji's food kind of separately so that she gets enough food. Otherwise, it's a problem. Thank you, everybody, for being here. Thank you. Oh, let me show you the book we've been reading. Here's the book, Brief History of Time, Stephen Hawking. We will be back with it tomorrow. We will be back with it tomorrow. We will be back tomorrow with the book. And yeah, we'll continue elementary particles. Basically, we're getting a good, nice crash course into the standard model with this chapter, so I really like it. And also, he is going into the spin property quite a bit, which I also like. By the way, if you see this live, first of all, rewind and see the whole thing. We covered an important topic today. Second of all, please do like the live, share, subscribe, share with your friends, family, coworkers, dogs, cats, neighbors, the President of America. Share with everybody. And subscribe and hit the bell icon so you get notification for when I go live. And can you please like the live? Can we get 30 likes? We got 20. But could we get 30? One of my bunnies is like that. She eats all Tommy's food. Oh. I thought Hawking's was all about black holes. Yes, we will get into Hawking's black hole work. He worked on black hole radiation. So yes, yes, you're correct. You're right. And he's from your same country. He's from the same country as you. So we will definitely get into his PhD work, which is the black hole radiation stuff. So we will definitely get into that. That'll be really, really interesting. For sure. He's basically putting down the foundation right now. He talked about the expanding universe, Big Bang, singularity, black hole singularity, remember? Then we gave an introduction to quantum mechanics and the uncertainty principle last night. And then today we started with the elementary particles, which will wrap up basically the basic foundation for particle physics and further quantum mechanics. And also tell us about the various matter particles, force particles, the how the matter particles interact, the spin property, all that. Those are all really good information to have. And then yes, Hawking radiation. Yes, you're right, because it's so important, because we already mentioned, but the Big Bang is a singularity. That's how we think the universe might have gotten started. And another singularity is actually black holes. So it will be very interesting to read about his work on that in general and this Hawking radiation stuff. So I'm sure he'll get into that in his book. So just keep on listening. We are laying the foundation. Basically, we'll keep talking about elementary particles, the particle stuff tomorrow, forces of nature tomorrow, and then we'll finish up this chapter. And then the very next chapter is called black holes. So we will, I'm sure, learn a lot about his exact view on black holes and what he contributed to black holes. Right here, chapter 6. Wow. Oh my gosh. My library receipt is right here. Well, there's going to be some really interesting stories in this black holes chapter. I can see it already. Black holes ain't so black is one of the chapter names. Oh my gosh. The origin and fate of the universe. The arrow of time. Goodness. Chapter 10 is wormholes and time travel. Oh, wormholes and time travel. The unification of physics. I love it. Lively and provocative, Mr. Hawking clearly possesses a natural teacher's gifts, easy, good-natured humor, and an ability to illustrate highly complex propositions with analogies plucked from daily life. Plucked from daily life. Goodness. Charming and lucid. A book of sunny brilliance. This book marries a child's wonder to a genius's intellect. We journey into Hawking's universe while marveling at his mind. He can explain the complexities of cosmological physics with an engaging combination of clarity and wit. His is a brain of extraordinary power. Baji right there. Baji has settled down, so I think Baji needed a snack. He got many snacks throughout the day, but currently he needed a snack. And so, see, now he's settled. Now he's settled. Baji right there. Physics book reading with Baji. We like analogies, okay. Brief History of Time has expertly guided non-scientists everywhere in the ongoing search for the tantalizing secrets at the heart of time and space. This edition makes vividly clear why Professor Hawking's eloquent classic has transformed our view of the universe. Indeed, it has. So yeah, I thought the hairband would look really weird and bad, but I kind of like it. I think I'm gonna keep wearing it sometimes when I feel like it. Okay, it looks so weird. Okay, there's a gap right there. Okay, that's fine. But the hairband black color is different than my hair's black color. I like that. You can see that black color can be of different types. I love it. Okay. Oh my gosh. We just got a snack, so we're gonna skip that snack. Does look a bit like a tiara. Oh, thank you. The chat has died down. Ooh, I skipped a page. I'm gonna read this part again. So the forces that they carry will only have a short range. Oh, here, this part. In quantum mechanics, the forces or interactions between matter particles are all supposed to be carried by particles of integer spin 0, 1, or 2. What happens is that a matter particle, such as an electron or a quark, emits a force-carrying particle. The recoil from this emission changes the velocity of the matter particle, of course. The force-carrying particle then collides with another matter particle and is absorbed. This collision changes the velocity of the second particle, just as if there had been a force between the two matter particles. It is an important property of the force-carrying particles that they do not obey the exclusion principle. That's right. I don't know if I made a note of that earlier or not, but it is extremely important. The force-carrying particles do not obey exclusion principle. This means that there is no, I believe it's just the fermions that obey exclusion principle. And those all have the spin 1/2 type of spin. This means that there is no limit to the number that can be exchanged, and so they can give rise to a strong force. However, if the force-carrying particles have a high mass, it will be difficult to produce and exchange them over a large distance. Good night. Good night to Belgium. Good night to the UK. If the force-carrying particles have a high mass, it will be difficult to produce and exchange them over a large distance. So the forces that they carry will only have a short range. On the other hand, if the force-carrying particles have no mass of their own, such as photons, no mass, the forces will be long range. That is true. The electromagnetic forces are long range. The force-carrying particles exchanged between matter particles are said to be the virtual particles, because unlike real particles, they cannot be directly detected by a particle detector. So if a particle detector is detecting it, then it's a real particle. If it's just being exchanged and stuff, it may not be considered a real particle, but it kind of is. We know they exist, however, because they do have a measurable effect. They give rise to forces between matter particles. Particles of spin 0, 1, or 2 do also exist in some circumstances as real particles when they can be directly detected. Then they appear to us as what a classical physicist would call waves, such as waves of light or gravitational waves. They may sometimes be emitted when matter particles interact with each other by exchanging virtual force-carrying particles. For example, the electric repulsive force between two electrons is due to the exchange of virtual photons. The electric repulsive force between two electrons is due to the exchange of virtual photons, which can never be directly detected. But if one electron moves past another, real photons may be given off, which we detect as light waves. How very interesting. How very interesting indeed. Thank you for being here. Welcome to the live. Can you please like the live? Can we get 30 likes? Force-carrying particles can be grouped into 4 categories according to the strength of the force that they carry and the particles with which they interact. It should be emphasized that this division into 4 classes is man-made. It is convenient for the construction of partial theories, but it may not correspond to anything deeper. Ultimately, most physicists hope to find a unified theory that will explain all 4 forces as different aspects of a single force. Indeed, many would say this is the prime goal of physics today. Remember that superstring theory is a candidate for a unifying theory. Too bad that it cannot be tested, but it is hoping to unify things. Indeed, many would say this is the prime goal of physics today. Recently, successful attempts have been made to unify 3 of the 4 categories of forces, and I shall describe these in this chapter. The question of the unification of the remaining category, gravity, we shall leave till later. So unifying gravity is hard. Unifying the 3, electromagnetic force, weak force, and strong force, sure, that there has been progress with that, but unifying gravity also is hard. First category is the gravitational force. So this is where we stopped. This is page 72 of A Brief History of Time by Stephen Hawking. This is where we stopped. I'll make a little page folding right here. I think we'll start from here tomorrow. Gravitational force. This force is universal. That is, every particle feels the force of gravity according to its mass or energy. Gravity is the weakest of the 4 forces by a long way. It is so weak that we would not notice it at all were it not for 2 special properties that it has. It can act over large distances, and it is always attractive. This means that the very weak gravitational forces between the individual particles in 2 large bodies, such as the Earth and the Sun, can all add up to produce a significant force. The other 3 forces are either short range or are sometimes attractive and sometimes repulsive, so they tend to cancel out. In the quantum mechanical way of looking at the gravitational field, the force between 2 matter particles is pictured as being carried by a particle of spin 2 called the graviton. We don't know if the graviton is really real or not. I don't believe we have found it, but if it were there, then that's what we call, that's what we would have. This has no mass of its own, so the force that it carries is long range. This has no mass of its own, so the force that it carries is long range. The gravitational force between the Sun and the Earth is ascribed to the exchange of gravitons between the particles that make up these 2 bodies. Although the exchanged particles are virtual, they certainly do produce a measurable effect. They make the Earth orbit the Sun. One would think that gravitation has an effect. Real gravitons make up what classical physicists would call gravitational waves, which are very weak and so difficult to detect that they have not yet been observed. Well, at the time of writing this book, it was not observed. Now we have observed gravitational waves, by the way, with the experiment called LIGO, laser interferometry, gravitational observatory, something like that. Laser interferometer, yeah, laser interferometry, gravitational observatory. We have now measured gravitational waves from cataclysmic events like neutron star, or neutron star black hole, or black hole mergers. So we do actually observe gravitational waves now as of 2000. Either 15 or 17 was the first one that we observed, and it was big news, big news, when we first directly measured gravitational waves. The next category is the electromagnetic force, which interacts with electrically charged particles like electrons and quarks, but not with uncharged particles such as gravitons. It is much stronger than the gravitational force. The electromagnetic force between two electrons is about 1 million, one with 42 zeros after it. So the number 42 is kind of significant here, isn't it? Stephen will like this. Stephen likes the number 42. I don't know if he's right now here or not. I will read this again tomorrow, Stephen, if you missed it. 1 with 42 zeros after it times bigger than the gravitational force. However, there are two kinds of electric charge, positive and negative. The force between two positive charges is repulsive, as is the force between two negative charges, but the force is attractive between a positive and a negative charge. A large body, such as the Earth or the Sun, contains nearly equal numbers of positive and negative charges. Thus, the attractive and repulsive forces between the individual particles nearly cancel each other out, and there is very little net electromagnetic force. However, on the small scales of atoms and molecules, electromagnetic forces dominate. The electromagnetic attraction between negatively charged electrons and positively charged protons in the nucleus causes the electrons to orbit the nucleus of the atom, just as gravitational attraction causes the Earth to orbit the Sun. The electromagnetic attraction is pictured as being caused by the exchange of large numbers of virtual massless particles of spin 1 called photons. Photons carry the electromagnetic force, and they're massless. Yay! Long distance force, massless photon. Long distance type of force being carried by a massless force particle carrier thingy thing. Sounds about right? Sounds about right? Again, the photons that are exchanged are virtual particles. However, when an electron changes from one allowed orbit to another, one nearer to the nucleus, energy is released and a real photon is emitted, which can be observed as visible light by the human eye if it has the right wavelength, or by a photon detector such as a photographic film. Equally, if a real photon collides with an atom, it may move an electron from an orbit nearer the nucleus to one farther away. This uses up the energy of the photon, so it is absorbed. That's all very cool. That is all very cool. Very cool indeed. Very, very cool indeed. Okay, it's 2 a.m. I gotta go. The third category is called the weak nuclear force. We're going to talk about this in more detail tomorrow. I love this though. It's hard to stop. It's hard. It's very, very hard. W bosons, Z bosons. We'll talk about this tomorrow. W bosons and Z bosons. Spontaneous symmetry breaking. This means that what appear to be a number of completely different particles at low energies are in fact found to be all the same type of particle, only in different states. Oh, my phone's about to die. Let me charge it. Thank you for the super chats tonight, guys. Really appreciate it. If you see this as a video upload later on, please do leave your likes and comments. Supers are always welcome. Thank you so much. Thank you. But please do leave your like and comment and share and subscribe and all of that good stuff. Thank you. I need to charge the phone. I think I'll do that right now. I have another phone over here which is partially broken. Let me put the phone to charging. Give me 1 second. Yeah, okay. Ooh, let me show you a picture actually while the phone charges. I can show you something. Don't have to waste time. Hello. Hello, hello, hello. Can you still hear me? If you're still there. Okay, actually I'll share the live. If you're seeing this live right now, please do rewind and watch the whole thing. Leave your comments, like, subscribe, share, and thank you so much. See you tomorrow. Here's a kitty cat. Actually, maybe I can show you Baji, but maybe not. Stay tuned. See you tomorrow. Bye. 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 See you. Good night.